I will give lecture. I will try to succeed with lecture today because I have simultaneously. I will have in 20 minutes some meeting. Okay, we will see. Maybe we will finalize early. So. Okay. Time. Oh, come on. Okay, so can you see my screen?
Yes.
Okay. So just a few words about Einstein, about yeah, we spoke about black holes. So we discovered that there is such interesting things around in the vicinity of these objects. And I would like also to say a few words about the consequence or observational things which we can discover due to general relativity, because of course when we build some theory we would like to be sure that this theory satisfies observational data. Of course, when Einstein built general relativity, of course he in the first check which prediction should be from general relativity and which explanation general relativity can give for already existing data. And so we can you can write the how call it, it's better to call it the observational consequence general relativity. So the first one, which is very important, and it was really some strange things in Newtonian theory. So this is shift of planet perihelion. So this what it means? It means that when we consider the motion of the particle or planet in the central field, so this particle or planet will move on ellipse. Okay, so we understand that this comes to us from the first Keplerian law. If we will take into account the general relativity effects, it means that we take into account that space is not a flat, but space is a curve. In this case, the trajectory will change, and trajectory will be like this. This trajectory, the type of such a kind of trajectory, called rosette trajectory. It means that all time we have a shift of the orbit. So I can, oh, so beautiful. I will write like this and like this. So we have a shift of this orbit on some angle delta, for example, delta psi, okay, delta theta. This exactly called the shift of planet perihelion. So perihelion, this is the nearest, if we say about planet, what is a perihelion, I will remind. Perihelion, when we have a planet, with sun, for example, and we have a planet, I will exaggerate and I will draw this orbit like this. So suggest this is ellipse, it should be ellipse. This is sun. This is, for example, planet. And the 2 points, this point and this point we call perihelion, and this apogelium, or pericenter and apocenter. So pericenter, this is nearest to the massive point, or to the to the sun, the nearest point of the planet. So this one. It's understandable, of course, if we have a shift of perihelion, it will be also shift of apogelium. So, but usually in the terminology we are using like this. And it was known from classical, it was known for and was measured for Mercury, that Mercury has this shift, which equal equal 33 angular seconds. So this is from observation, and it was really complicated to explain in the framework of Newtonian mechanics. So I already said you in the beginning of the lecture that it was invented even in another planet. So this is for Mercury. So it was even invented another. What's happened? And this explanation was given in general relativity. So if you will find this angle from general relativity, I just will write the final expression. You can find the explanation in detail how to obtain it in our book, Foundation of Celestial Mechanics. So I will write the final expression. This is this one, where Rg, this is gravitational radius. A, this is major semi-axis of the orbit. So if this is the center, A, this is this one. E, this is eccentricity. So, and this expression appeared in general relativity. We can obtain it. And for the Mercury, it means when M equal mass of sun, if we will put and all major semi-axis and eccentricity for the Mercury, so we will obtain exactly this shift of the angle, exactly 33 seconds. So it was the first test for general relativity, and this test shows that really what general relativity is represent is really correspond to observational data. So general relativity can explain this shift of perihelion of planet, and it's understandable that much more higher value this is for Mercury, and of course each planet has this shift, but as far as the planet from the sun, the shift will be less. It's understandable. And this, and we call sometimes relativistic shift of perihelion. So the reason why we have this additional 33 seconds, which we can't find in classical mechanics, this is exactly due to the fact that space is not flat. So this is influence of the curvature of the space. It means that sun around Hello? Hello? I'm apologize, but I need to interrupt our lectures, and we can continue today in any time if you can, because now I need to go to this meeting, which is very important. So, what can
Maybe
you?
we'll make next lecture longer. It will be on Friday for Sphere. If
I I'm scared that on Friday it can be also problem, because on Friday I have
So, can I ask you, the lecture which must be tomorrow, it is corresponding as this lecture or another?
no, tomorrow we can make this lecture if you can be free tomorrow, so we can continue tomorrow.
Because I thought that we already
Yes.
choose the time
Yeah.
for
You already choose
Sphere
time.
tomorrow.
Super.
So, and
Okay, please write me
Okay.
this time, okay? Because I didn't receive from your message. I just by chance I saw that I can succeed with the lectures today, but I can see that it's not like this. Now I need really to run. Please write me the time and when we can meet with these lectures, because we already need start with the metric of our universe, and we will meet with you when you can. Okay. So if it will be tomorrow, anytime for me is okay. Okay. Wait from your some message.
okay.
Okay, I am apologize really, but I really need to run very quickly. So good day. So and see you later. Ciao, ciao.
Goodbye.